All right. Good morning, everyone. Happy Monday. Hope everyone's had an excellent weekend. Um, so, in terms of what we got coming forward for us this week, you got a video homework due later tonight if you haven't already sent that my direction. We're not going to be talking much more about Ampere's Law today. I just have like a quick sort of last example that I left on the slides from last class, but we didn't really get a chance to cover it. So I thought we'd talk about it real fast just in case it helps you come up with a different type of Ampere's Law problem that you could look at. And otherwise, we'll be back having web work on Wednesday, sort of as per usual. Lab this week is on Faraday's Law, which is what we're going to be talking about today. So you should have everything, should be fresh in your mind in terms of taking all that into lab tomorrow. On Friday, we'll probably maybe finish up just a little bit with Faraday. We're only spending pretty much one day, maybe in a little bit, on that chapter, and then we'll be starting in on chapter 23 on Wednesday, and looking at sort of bringing together all these laws and sort of discussing the other types of things that we can figure out, kind of about them. Otherwise, the plan at the moment is to have test 3 basically 1 week from Friday. My initial gut is that I'd like that to kind of go the same way. Clearly, I need to get your feedback on the last one before we can really talk about that. So I'm almost done with some other grading that I had to get done before I could score those. I'm hoping to have all those to you by Friday, so that I can make informed decisions about if we want it to look the exact same, or if anything's going to change or anything along those lines. But kind of be tentatively planning at least that a week from Friday is going to be when some sort of test material is going to be due. Most likely similar to what we did for test 2. Otherwise, just a reminder, despite the fact that everything is remote, we are still basically not having classes on the day of SSRD. And so 1 week from Wednesday, we will not be having class. So next week we just have a Monday and a Friday class, unless the Friday we're taking up with a test. So pretty much next week it'll just be Monday, then in that case. And then, of course, polling, as per usual. Okay, so I thought we'd start today with like a quick review of Ampere, make sure we're feeling okay-ish about that, and then we'll launch into yet another sort of new law. But safe to say this pretty much rounds out most of the new type laws like this that we're going to be talking about. So we had Gauss's law, then we had Ampere's law. Today we're going to be talking about Faraday's law, and then we're pretty much through kind of all the heavy hitters in that sense. So thought we'd start off with a quick little review, just playing around with Ampere. So thought I would pose to you the situation where we have a wire to the right, so that's the really thick black line that's kind of doing this wavy thing. It's carrying a 5 amp current, and that current is traveling in the direction given by the arrow, so it's like up and then down and up. And my question to you is that if we took a loop, sort of indicated by the hoop there, and we integrated around it the value of b dot dl in the direction indicated, so with the little arrows going around the loop in that direction, what would we find for that particular value? Like what would be the total that we would get in that situation? Okay, I'll give you a few minutes for that, and then we will talk about it, do a little bit more Ampere's law example, and then we will move on. Okay. All right. I think pretty much everyone has answers in at this point in time. So let's check those out and then talk about it some. Stop. All right, we got about 75% of you for B and then a little bit for the others. So, this problem, pretty much just a almost definition type problem of what is Ampere's law actually telling us for these type of situations and for these types of problems. So the main thing to keep in mind with Ampere's law is what Ampere's law really says is it basically tells us that, you know, the integral of B dot dl, so going around a closed loop, adding up all the contributions of B in the direction that we're traveling, is equal to mu naught times the I enclosed. So mu naught just being the constant, and the I enclosed being the amount of current that we have enclosed within the loop. And remember that we basically defined enclosed here as, you could imagine it just as being any current that sort of pierces the bubble or the sort of soap film that you would make, sort of stretching it over your loop in question. Now, remember here that an important idea was because you could have current going through both directions, we needed to decide what direction are we going to call positive enclosed current. And we decided that we would dictate that purely based off of right-hand rule. So the idea being that if we're going around the loop, the direction of positive current is given by right-hand rule. So if you curl your fingers in the direction that you're integrating around the loop, your thumb points in the direction of positive current as far as you're concerned. So in our case here, we're sort of integrating around the loop in a, what I guess would be counterclockwise fashion when viewed from above, looking down. So if I curled my fingers in that counterclockwise fashion, my thumb would be pointing up, telling me that positive current here is going to be current that's going in the upwards direction. And then it's just a question of, you know, keeping track of all the different places that I have current piercing my loop. So in this case, you know, here I cross the loop going upwards, so that's going to be positive contribution. Over here, I cross the loop going downwards, so that's going to be negative contribution. And then over here, I again cross my loop going upwards, so that's going to be a positive contribution. It's the same wire, it's the same current throughout the whole thing. So by that reasoning, you know, essentially we get that, say, these two are just going to cancel with one another, one up, one down. And so we're going to get left with just a net enclosed current of one going upwards. And so therefore, if our, you know, wire was carrying 5 amps, then we get a positive 5 going upwards. Don't forget the mu naught that's there, and therefore B, I guess, would have been the answer that we're going for here in the end. Your units of this, since it's always basically a magnetic field times a distance that you're traveling around, is a Tesla meter, which I don't think is represented by any other unit in E&M, although it's tough to keep track of them all. Okay, so that was just sort of your raw sort of bread and butter, like this is Ampere's law when we're looking at it. So I want to look at one other example before we jump into something new, which is that in many cases when we're using Ampere's law, we're taking advantage of nice symmetry arguments, and so that we can, you know, make some idea of saying, oh, my magnetic field is constant along my loop, so I can pull it out. Or, oh, my magnetic field is always pointing in the same direction around my loop, so I don't have to worry about that dot product. Those sorts of things. But for sort of more contrived type problems, it doesn't necessarily have to follow that exact symmetry. Remember, Ampere's law holds true regardless of what the geometric circumstances are in the problem. It's just easiest for us to work with normally when the symmetries are nice. So for an example of that, let's take something that looks maybe a bit more like this. So we have this situation where we have this loop that's this square rectangle in this case. I guess it's not really square, it's just a rectangle in this case. And via whatever on earth is happening inside this loop, we're getting this really sort of crazy magnetic field measurements along each of the four sides of the loop. Now, to actually achieve this sort of weird configuration with like the magnetic fields of this strength and this angle, you would need some insanely complicated interior currents going through the whole thing, right? But what we can sort of conclude is just from sort of integrating our way around this loop, no matter which way we decide to go, we can decide, well, what is the net current in the interior? Say, is more of it flowing upwards or out at us, or is more of it flowing into the loop and into the page at us? Okay? And again, it's just largely a question of breaking it up into its various individual components. So if we jump over to a board here, let me bring myself in. Let me bring the slide in so we can remind ourselves what that's looking like. So the idea here is that what we want to do is we want to take advantage of the fact that, again, we know that mu naught times our I enclosed equals our closed integral around the loop, right? And in this case, we have a rectangle that we're going to be going around, so it is closed, so we're good on that front. What's not true, for sure, is that B and DL are not going to be pointing in the same direction in each case, because they change all over the place. And B is not even the same magnitude in all cases. Like in some sections, it's a little bit stronger than in other sections, right? So it's not a case where we could super simplify that right side integral when we're looking at things. But it is a case where we could sort of individually evaluate it along each of sort of the four sections where things are a bit more consistent across that section. So basically, like, what does it look like on the top, plus what does it look like on the side, plus what does it look like on the bottom, plus what does it look like on the other side, the left side, for instance. Okay? So instead of looking at this as an integral, I could basically look at it as sort of saying, well, I want to look at and say, well, what is B dot DL along the top, plus what is B dot DL along the right-hand side, and so on and so forth. So plus B dot DL along the bottom, and then plus B dot DL along the left-hand side, right? So literally just breaking sort of the integral up into its individual discrete parts. And along each of those parts, I know that B is at least constant along that section. I know that B and DL are at least pointing consistently with respect to one another along that section. Okay? And so really, I guess instead of writing DL for all these, I should have just written sort of that side length in each individual case. So here, we can, write out what those individual pieces are as we go along. Remember that so I guess technically speaking, I'd still have like an integral here. Since they're DL still. So along the top, for instance, I can say that, well, along the top, when I take B is constant, so I can pull it out of the integral. So then when I take the integral of DL, that's just going to give me whatever that width is. All right? So let's go ahead and call, left and right, that length the width, and up and down, we'll call that length the height, just so we can attach some numbers to it here. So that means along the top, I'm going to get whatever my magnetic field is along the top, dotted with whatever my total length is, right? But I can always write that out as just in terms of magnitude. So I can say this is just the magnitude of B at the top times the width, so the whole length along the top, times the cosine of the angle in between those two things. Well, on the top, basically, you can imagine that we didn't specify which direction we're going around our loop here. Remember, you always got to specify a direction that you're actually traveling around your loop in any given circumstance. Here I'm going to move this down a bit so we can see it. Here, it's totally up to us which way we want to go around. Initially here, I'm just going to kind of imagine that we're going around clockwise. So I'm saying that we're going around in this direction. So when we're up here at the top, DL is pointing in that same direction. So DL is always pointing in the direction that we're traveling along each stretch. So up on the top, DL is pointing that direction, B is pointing straight up, and therefore our cosine of the angle between those, the angle between those is just 90 degrees. It's going to end up being 0. Cosine of 90. All right, and we can just repeat that, the whole way around here. So then on the right-hand side, I can say, well, on the right-hand side, I'm going to have my B on the, holy smokes, sorry about that. Let's try that again. B on the right times the height that we're going down times the angle between them. Well, on that side, B is kind of going off at this angle down here. DL is moving straight down. The angle between those I actually gave you in this case, and we said that it was 60 degrees. Okay, and then we just keep on moving around. So on the bottom, we got B on the bottom times the width again, because that's the length that we're traveling over. And on the bottom, the angle is, of course, just going to be 0 because they're pointing in the same direction. Both of them are pointing to the left there. The B field's pointing to the left, and we are traveling to the left down there. So that would be a cosine of 0 degrees. And then lastly, we have on the left, we got our B field to the left, we got our H for the height going upwards, and then yet again on the left, the angle between those two things would be, or we're told, is 60 degrees. Okay? And then it's pretty much just a question of plugging things in, at that point in time. We know all those things. We know the value of mu naught up there. And so we can go ahead and, solve things around for I enclosed. So just by example here, B top we said is, hopefully I can read these, 3 Teslas. Our width was 20 centimeters, so that's 20 times 10 to the negative 2. Cosine of 90 is, of course, just 0, so I guess that didn't really matter. On the right side, we have 0.5 Tesla. Our height over there is 10 centimeters, 10 times negative 2, and cosine of 60. I'm just going to keep writing these down here so we have space. On the bottom, we have 0.25 Tesla times our width again, so that's 20 times 10 to the negative 2. And down here, we got cosine of 0, which is just 1. And then finally, on our last side, we again had 0.5 Tesla. Our height is 10 centimeters, and our angle again was cosine of 60. Okay? And so when we put all of that together, then here, we would just crunch that number and then divide by mu naught. So divide by 4 pi times 10 to the negative 7th. And when I plug in those numbers, I get something that looks like a 79.6 kiloamps. 79.6 kiloamps. As I'm going around here. Note, this is positive, right? So what direction is positive current according to the direction I went around the loop? Well, I decided to go around the loop in this clockwise direction here. So wrapping my fingers in the clockwise direction, positive would be pointing into the page. And so we would say, because I got a positive number here, I would say, oh, this must be pointing into the page. If I'd gotten a negative number, I would have known it was pointing the opposite direction. And that's why even if I were to integrate around the loop in the opposite direction, if I was to integrate around the loop in a counterclockwise direction, all that would happen is that we would end up getting a negative value, and then we would say, oh, if I went around in a counterclockwise direction, positive would have been at me. I got a negative, so therefore it's pointing into the page. So you'll get the same direction no matter what. But I highly recommend you get in the habit of making it very clear what direction you're going around the loop in different problems. Okay? That's the crux of Ampere's law. That's how it works. It tells us sort of what the magnetic field is based off of the enclosed current inside a particular loop. So, summarize a few things here with respect to Gauss and Ampere, because it kind of wraps up what we wanted to look at with respect to both of those. But they kind of have a lot of similarities between them in terms of sort of what they're saying, and also in terms of when they're useful to us. So realize here that what Gauss's law basically did is it related electric fields to the source charges, which is exactly what like our Coulomb's law was doing previously, right? So in that sense, there's no real new information being given there. It's just an alternative way of seeing the relationship between these two things, between the sources that make the fields and the fields themselves. And similarly, Ampere's law is relating the magnetic field to the current, which is, again, basically just looking at sort of what Biot-Savart told us. Biot-Savart, our original way of writing it, related Q times V, but we also saw later that we can write that in terms of the current. So in both cases, it's relating moving charges to the created magnetic field. And again, it's just kind of a different way of looking at the same thing. For our purposes, many times we can only really take advantage of sort of the power of Gauss's law and Ampere's law in cases when we kind of have nice symmetries in the problem, that we can actually do those sort of left-hand side integrals easily. But it doesn't come up as much for us, but technically Gauss and Ampere's law are sort of better formulations of these relationships between the sources and the fields themselves, because Gauss and Ampere's law still hold true basically under all circumstances. Whereas when we start looking at things that are moving at really, really, really high speeds, really, really fast speeds, Coulomb's law and sort of Biot-Savart kind of tend to start breaking down a little bit. They don't really give us as good of an inclination of what's happening. So Gauss and Ampere's law are kind of sort of the more general, big picture, always applicable situations. The whole reason we started with Coulomb's law and Biot-Savart is because they're generally a little bit easier for us to sort of understand what's happening in a particular situation when we're looking at it. Okay? From here, though, I want to sort of go to something different. And you probably can tell that it's going to be something different because everything we've talked about this semester thus far has been, how do I relate sources to fields and the forces those fields exert? That's where we started with electric fields and the forces those electric fields exert. And then we've added on magnetic fields, how they're related to moving charges, and the forces those fields exert. So we've kind of covered, both of those sides of things. We've covered the electricity side of things and the electric fields. We've covered the magnetic field side of things. Something we haven't covered as much is the relationships between the two things. And largely the reason for that is because the relationships between the two things were discovered far, far after the fact of the two individual things themselves. So people were making measurements of electric field and ideas of current and being able to put compasses near things and see how the magnetic field is related far, far before they sort of realized that there's more interactions between the two things. The only interaction sort of thus far that we've mentioned about sort of the fact that there might actually be a relationship between magnetic fields and electric fields was when we noticed that magnetic fields depend on a velocity, and velocity can be relative to an observer. So that if I have an observer moving at different speeds, he's going to see the charges moving at different velocities. And so in some cases we get an electric field, and in some cases we get an electric field plus a magnetic field, depending on how fast the person is moving, which is a bit of a conundrum and kind of tells us right away that there's got to be some sort of tie-in between the two that we're maybe not clearly seeing at the moment. And in fact, what we're going to talk about now was just first observed experimentally. It was not something that was, come upon theoretically, or that people realized that, there should be this relationship. It was something that was an accidental discovery. It was just observed, experimentally, and then Faraday kept playing around with it some more until he, gets a law named after him. So basically what Faraday found was he was playing around with currents running through little solenoids, right? So current running through a solenoid is going to create a little magnetic field. And what he found was that when he had one sort of setup with a solenoid, like the one I have sketched here, and he ran a current through it, and it created a magnetic field, if he had another solenoid just sitting nearby, for a brief moment of time, even though the two were in no way connected, he would observe a current running through that other solenoid. And what he realized is that the times that he observed that current running through the other solenoid was basically whenever he flicked the switch to turn on and off the current in his other solenoid. So he flicks the switch, turns the current on, boom, gets a little blip of current in his other device that's totally unattached. And then he turns the current off. Boom, he gets another little blip of current in his other device. Interestingly enough, in the other direction this time. And he found it didn't really matter sort of how he, oriented the solenoids or any of these sorts of things. Whenever he flicked on the switch or whenever he flicked off the switch, he'd get this little blip in current. The rest of the time, he got nothing. And so we can kind of summarize that with a bit of directionality here with my lovely picture over here. And so the idea was that as long as there was a constant current creating a constant magnetic field, nothing special was happening. The only time something interesting happened was when there was, a change in the current. He flicked the switch off or he flicked the switch on, which would, of course, created a changing magnetic field, because once there was no field and now there is a field, or there is a field and now there's no field, right? So it's turning the field on or off. And so what he found is basically here I've sort of sketched it out in the sense that, so if the field was coming out of the page at us, when the field was increasing, like if it was getting stronger pointing out of the page, he observed a current flowing in the, I guess that would be clockwise direction here, which would have told us that the E field was also swirling in that same direction. And then when the current, then when the magnetic field decreased, so when he flicked the switch off, for instance, he got it pointing in the other direction. So now the current was swirling around in the counterclockwise direction. And if he flipped his, other coil around so that the magnetic field was maybe going into the page, for instance, he basically got sort of a flipped case of that. So now when the magnetic field was pointing into the page, if it was increasing, he got things going around clockwise. But when it was decreasing, he got them going in the opposite direction, counterclockwise. So a few things that we can sort of deduce from this, just, and that Faraday deduced from it, just from the experiment itself. One, changing magnetic fields seem to induce or create currents. And of course, the only way we get a current is if we have an electric field. So a changing magnetic field seems to create an electric field. All right? So that's probably potentially maybe the main takeaway of Faraday. Changing magnetic fields create electric fields. And they don't just create any electric field, they actually create swirly electric fields. So like electric fields that move in loops. We're driving a current through a perfect little loop. Whoopsie. Through a perfect little loop over here as we're going around. We saw that for static charges, you can't get circular electric fields. They always have, they come out at one point, they end at another point. This is one way this is the only way, actually, that you can get swirly electric fields like this, is if you have changing magnetic fields. Now, there's something else that we can deduce from this, which is something kind of weird is going on with the direction of things. So, if we're thinking about changing magnetic fields here, we need to be saying, well, like, oh, okay, so if we're looking, in this case over here, where the magnetic field was increasing, we got something that was pointing counterclockwise, or that's clockwise. But when it was decreasing, we got it going counterclockwise. Perhaps unsurprisingly, we're going to want to relate this back to right-hand rules at some point in time. Right-hand rule governs pretty much all things having to do with magnetic field commonly. And one of the ways that we can see it is that if we were to say, oh, my magnetic field is increasing. So let me try pointing my thumb in the direction of increasing magnetic field. Oh, but if I do that, my fingers curl counterclockwise, which is not what we saw here. But it's actually the opposite of it. And in fact, it's the opposite of it in every single case. Like if my B field is getting bigger, pointing at me, it's curling the opposite of that. So it would be curling clockwise. If my B field is getting less, so like my change in B would be getting negative, for instance, and pointing into the page, then my fingers would curl clockwise. The opposite of that would be counterclockwise. Okay? So there is a sort of rhyme or reason to this directionality that's going on here. It is just going to be related to right-hand rule again. It's a little bit more cumbersome in the fact that it's related to right-hand rule with sort of an extra negative sign thrown in there. It's like the opposite of the right-hand rule. Which if you wanted to play a dangerous game, you could think of as being the left-hand rule, but that's opening the door for you to confuse yourself at some point in time. So the main takeaways here is that when we are trying to figure out the direction of these, a common way to think about it is that the electric field that gets created, or another way to put it is that the current that would get driven by this induced electric field is always going to be a current which is going to oppose the change in the magnetic field. Okay? You can almost think of this in the sense that you can kind of, attach a colloquialism to it in the sense that, like, nature abhors changes in this case. So if you start trying to change the magnetic field, basically nature doesn't like that. And it tries to induce this electric field that's going to oppose that change. Okay? So how can I sort of most easily describe this, maybe with a few pictures here, just to see if we can make sure that this is making some semblance of sense. So imagine here that I had a magnetic field pointing that way, say at time equals 0, and then at time equals 1, so like 1 second later, my magnetic field, is now this big. At time equals 1, for instance. So if I was looking at, what's my change in the magnetic field over time, I would say, my magnetic field grew basically that much in 1 second. So you could imagine that this little thing would be my dB dt. Like, that's how much my magnetic field grew in that little chunk of time. That would be pointing upwards, right? So we're getting more field pointing upwards. Nature's going to oppose that change. So the other way you can think about it is that nature does not want a magnetic field being induced upwards. Therefore, it is going to create something that would create a magnetic field being induced downwards. It's going to resist that change in the upwards magnetic field. So you can imagine that nature is going to want to oppose that with its own, like, be induced. Now, where is that be induced going to come from? Well, it's going to come from a little loop of current. It's going to come from a little curling electric field. And what direction is that curling electric field going to point? Well, I know how magnetic fields relate to electric fields. And so I can say, well, if I point my thumb downwards, because that's the direction of the induced magnetic field, my fingers are going to curl around, I guess in this sense, they'd be moving to the left in the front and to the right in the back. So it'd be clockwise when viewed from above. So my field, my electric field that's going to get induced is going to be something that, swirls around like this. Would be the resulting electric field. So Faraday's law tells us that the induced electric fields are always going to be induced in a direction that they will oppose the changing magnetic field. So note, when you're looking at these, you need to keep track of two different things. You need to keep track of what direction is the magnetic field pointing, and then you need to keep track of, and is it getting bigger or is it getting smaller? Because both of those two things factor into what direction is the changing magnetic field pointing. And that's what matters for you figuring out the direction of the current, or the direction of the electric field. Okay? Now we can add a little bit more sort of spice onto that, I guess, by realizing that earlier this semester, when we looked at things, we saw that just placed charges cannot create curling electric fields. All right? And therefore, we were always thinking of it in the sense that, if I follow an electric field around in a closed loop, I always get a total change in the potential of 0. That was our whole idea behind, how we analyze circuits and all these sorts of things. So when we're thinking of these curling electric fields, it's probably going to be useful for us to sort of distinguish them from, like, the electric fields we get from just stationary charges sitting there. And so we'll go ahead and we can call these like the non-Coulombic electric fields, or NCs, as we're looking at them. And so if we think about it, we could imagine that, if we were to integrate around, one of these non-Coulombic electric fields, one of these curling electric fields, we're not going to get 0 when we end up back where we started. We're going to get some positive or negative value, depending on which way we went around. And so, what does that look like? We can imagine if I integrate, around the closed loop. So if I integrate the field here around some closed loop, I'm going to get some particular value. If it's like a perfect curling circular system here, we could say, the circumference of the loop as I go around it is just going to be the circumference of a circle. And this, would be whatever the strength of that electric field is. And it's going to be related to some, like we could talk about it as being related to some potential. And so actually, there's 3 different ways you'll see Faraday's law sort of referred to. In general, the main sort of interplay is that changing magnetic fields create curling electric fields. But the fact that you get a curling electric field means that frequently, if you were to put a wire there, you'll get a current going through the wire. So people will oftentimes talk about the current induced. And if you're getting a current induced through a wire, we're used to thinking about currents and wires being related to a potential difference or an EMF that's driving that current through the wire. So you'll oftentimes also hear people sort of refer to the induced voltage from Faraday's law in these cases. So just remember that the base case is that changing magnetic fields are creating a swirling electric field, but swirling electric fields kind of give rise to currents, and we like to talk about currents in terms of voltages, so that's still kind of what we're looking at in these cases. All right, so to put it all together here, and then we'll look at a few examples, and hopefully you'll be set for lab tomorrow. If we put it all together, sort of all the separate ideas that we've basically already talked about, so like the directionality and sort of the strength of it, those sorts of things. So Faraday's law relates the curling electric field to the amount, let me put it differently, to the amount of changing magnetic flux through a surface. Okay? So you can imagine if we have, a circular surface here, and I have magnetic field pointing through that surface, and say I start turning up the dial so that the magnetic field starts getting stronger and stronger and stronger. In that case, I have more magnetic field going upwards through the surface. I would want to resist that. So I'm getting more going up, so turn your thumb upside down. That's the role that this minus sign here is playing. This minus sign is important in Faraday's law. That's what tells you that it's resisting the change in magnetic flux. So I turn that thumb upside down, and then I can imagine basically just saying, well, what is the flux through this surface? The changing flux through the surface gets you the strength of the electric field. Right-hand rule will get you the direction. So I resist it. Fingers are going to curl, in this case, clockwise. And so that's the direction I would get my current going around as I was resisting it. Now, in terms of, what just happened over here with, that left-hand side of the equation, realize that instead of writing it as the, E non-Coulombic part dotted with dl, technically, since the Coulombic part, as we go in a circle, has to add up to 0 anyway, we can just talk about E in general, where E is, both the Coulombic contributions and the non-Coulombic contributions, because the Coulombic parts would go to 0 when we added them up anyway. So we're just kind of writing it a little bit more generally in that sense as we're doing it. If you want to, directly relate it to electric fields and those sorts of things, you'll usually want to sort of start with like the full nitty-gritty version of the whole thing. Excuse me. Frequently, though, people like to talk about the induced EMF or the induced voltage from this, and so this is kind of like the shorthand version that you'll see people commonly using for these sorts of problems. Okay? Note, this is still related to flux, right? We're back to talking about flux, magnetic flux through a loop. So, there's a variety of ways, and what we're curious about, of course, is the changing magnetic flux. So, how can we change the flux? Like, what are the various ways we can get a changing flux in a problem? Well, there's basically three ways. If you figure that flux is basically d dot A, or d dot dA, I could write that out as, magnitude of B times the magnitude of A times the cosine of the angle between them. If any of those three things change, I'm going to be getting a changing flux. So if I have a magnetic field that is changing with time, which is kind of the examples we've just been looking at, right? So, over time, I'm turning up the dial, my magnetic field's getting stronger. That's clearly going to create a changing flux. Other ways, though, that we can get a changing flux, if my area in question is changing. So maybe I have a loop of wire that's slowly getting smaller and smaller and smaller and smaller. Smaller and smaller and smaller loop of wire would mean smaller and smaller flux through the wire, which is going to create a changing flux and is therefore going to create an induced EMF. And then the other option, of course, is if the angle between those things changes. So if B is, originally pointing this way and my loop is this way, so that its normal would be pointing straight up, maybe they're both in the same direction. But then if I take my loop and I rotate it by 90 degrees, so that now my loop's normal is pointing this way and my my magnetic field is pointing straight up, now those two things are perpendicular to one another. Now there's no flux through the loop. So just by doing a rotation, thank you for that, by the way. Good call. Turned off the camera. Sorry. So if I have my magnetic field pointing upwards here, and I had my loop like so that it was also, the normal to the loop was also pointing upwards, initially those two things would be in the same direction. And so I would, have some amount of flux going through the loop, depending on how much magnetic field I had. But if I then took that loop and rotated it 90 degrees, so that now my normal to the surface is pointing to the right, and my magnetic field is still pointing upwards, well, now those two things are perpendicular to one another. So there's no flux through my loop. So just rotating the relative sort of loops that we're looking at relative to the magnetic field can also create a changing flux in these situations. If you have any of those things going on, you are going to get a changing flux, and therefore you are going to get an induced EMF. You're going to get curly electric fields being induced in the situation. So let's look at least one, maybe two, different sort of ways this shows up. The first one, we can actually check because we kind of have already done this problem in a different way. So for the first one, let's look at the situation where we are back to looking like at our situation here where we got like this bar sliding through a magnetic field. Okay? Previously, we did this with the idea of motional EMFs. And we said like, oh, this bar is moving through the magnetic field, therefore it's got charges. Those charges are going to feel a force from the magnetic field. They're going to get pushed up or downwards, and that's going to basically make the bar look like a battery and drive a current through our system. That's still not a bad way of looking at what's happening in this problem. But we have another way that we could look at it that actually might be a little bit simpler now that we have these ideas of Faraday's law. So by Faraday's law, we could argue, and I think I can just draw this on the slide itself here. We could argue that, oh, well, what I have here, is a loop, and I have a certain amount of magnetic field, pointing into the page on the interior of that loop. So I can talk about what is the flux of the magnetic field through my loop? And that flux in general, is just going to look like sort of how we would normally envision it. I could say, oh, my flux, and now that we have magnetic flux and electric flux, frequently we'll use a sub B to indicate magnetic flux. So my magnetic flux through the loop is just going to be, well, however strong my magnetic field is, times the area of my loop, times the cosine of the angle in between them. In this particular case, B is pointing into the page. A, we can sort of envision whichever way we want in terms of what way we want to be sort of integrating around our loop. But we can say A is into the page as well here. And as a result, we would say, oh, well, those two things are actually in the same direction then. So it would be cosine of 0, which is, of course, just 1. And A itself, I could say, oh, well, that's just, width times height. Width times height. So my flux through the loop would just be the magnetic field, times the width times the height. Just area of a rectangle. So now if I wanted to know what's the EMF induced about this loop, I can use Faraday to say, oh, well, I know the EMF is the negative change in flux over the change in time. Okay? Or in other words, it's the negative, and actually this negative is really only there to give us information about the direction of the EMF, of the current that's flowing around it. If you're just trying to figure out the magnitude, which is kind of what we're initially doing here, that negative isn't really telling you anything different. Negatives don't matter for magnitudes. So frequently you'll see that dropped, by the way, just when you're looking at magnitudes. But my flux here was, of course, B times W times H. Okay? I'm going to need to take that derivative inside that. It's that derivative of B times W times H. Which is therefore immediately going to beg the question, well, what is actually changing with time? B is not. B is just, into the page, whatever it is, that's not changing with time. So it could come out of the derivative. Similarly, H is not changing with time, right? I don't care however long I wait and this bar, slides to the right. H is still H. It's not like the bars are getting farther apart as time goes on or anything like that. They're parallel to one another. So it's just going to keep on, being the same value it was all along. So H is also going to be a constant. But what is not going to be a constant is going to be W. Because, at time equals 0, for instance, W's maybe, say, 1 meter. But then the bar is sliding to the right. So, at time 2 seconds, the bar is going to be farther along in that direction. So W will have gotten bigger. So W is going to be getting bigger as time goes on. So I will leave that time derivative with W. So I'll say it's going to be dW dt. But dW dt, that's just like a change in position over a change in time. This is just a velocity. And so we could also say that, oh, this induced EMF that we're going to get here is just going to be, oh, B times H times V. Where the velocity would be the velocity of the bar here. And that is exactly what we got when we did this with motional EMFs previously. Okay? So, on the one hand, Faraday's law just gives us sort of another way of understanding what's going on with these sorts of motional EMF type problems. But it's actually much more general than what we originally got for motional EMFs. Like Faraday's law will predict far more things than we could have just predicted for motional EMFs. And I'll look at another example of that on Wednesday. But I think you should be good with these notions in mind to sort of get through lab tomorrow. Just remember, it's always all about what direction is, like, am I getting more magnetic field through my surface, or am I getting less magnetic field through my surface? And then just remembering that if you always want to oppose that change in terms of the direction of your electric fields. Okay? Is that velocity a vector or just magnitude? Technically, we're just looking at things in terms of magnitude at the end. The other way that you could think about it is that up top here, when we sort of wrote it out as B times A times cosine, that's the magnitude of B times the magnitude of A times the angle between them. So we'd already kind of switched the magnitudes up there. So it's technically just the magnitude of the velocity down below. Okay. So in terms of whether or not they point the same direction, you have a choice in terms of, so the area always has to point sort of normal to your surface that you have. So our surface here is in like the XY plane. So we could argue either that the area is pointing out of the page at us or into the page away from us. As far as the magnitude is concerned, it won't matter. If you're trying to figure out the direction of the current, it will matter, but you just need to be consistent the whole way through. So for instance, in this case, I said my magnetic field, or the area, was positive going into the page. So I would have essentially said that I am integrating around my loop in the clockwise direction. Because by right-hand rule, if I curl my fingers in that direction, my thumb would be pointing into the page. Which means that I'm getting more flux going into the page, and therefore I would then go ahead and say, oh, I'm getting more flux into the page, I want to oppose that. Thumb goes the other direction. The current that I'm going to get is going to swirl counterclockwise in this situation. So the direction of whether you make your area go into the out of the page sort of really only matters if you're going to be really careful about trying to do everything in terms of like this negative sign here. In general, I really recommend for Faraday's law problems, use sort of Faraday's law itself to figure out the magnitude of things, and then use the idea that, and your right-hand rule, that you're opposing those changes to figure out the direction when you're doing these sorts of things. Okay. I'm going to leave things at there, at least for today. I'll get a web work up basically after class this afternoon, so you can start looking at it for Wednesday. If you got any questions or things that come up, let me know. Email or Campus Wire is the best spots. And otherwise, have fun in lab tomorrow, and I will see you on Wednesday. Take care, all.